For this problem, we're given that there is a long cylinder with radius r. I've drawn that up here, and I've excluded the caps to show how long it is. And there's my radius r, and we're given also that at any point a distance r from the central axis, right here, the volume charge density is given as rho of r equals ar cubed. And I tried to illustrate this by showing how as r increases, the rho, the volume charge density, increases exponentially until it gets to the end of the cylinder. So let's see here, in terms of A, little r, and big R, and appropriate constants, use Gauss's law to find the magnitude and direction of electric field for A at points inside the cylinder where little r is less than big R. And so I illustrated this. I have the original cylinder here. I've given it an arbitrary length L because it's impossible to denote a length to an infinitely long cylinder. So I'm just going to use this arbitrary length L for now and then apply it to the infinitely long cylinder. And so you see I have the original cylinder here of length capital R, and then I've made a Gaussian surface of a smaller cylinder of length little r, where little r is clearly smaller than big R. And so now we're going to try to solve for the magnitude and direction of the electric field. And so I start out with something that we've learned, that dq equals rho dv. And so the v in this case would be the volume of the cylinder, of the small cylinder. And so that would equal pi r squared times L, the arbitrary length that I've given. And so to find dv, I just take the derivative of that to get 2 pi r dr times L. And so then I plug that dv into the equation, and then I come out with dq equals rho times 2 pi r L times dr. And then if I want to solve for q, I have to take the integral of that, so the integral of dq is q, and then I take the integral of the other side from 0 to r, as my integration constants, of rho times 2 pi r L dr, and that equals integral of from 0 to r of ar cubed. I just plugged in my original rho of r equals ar cubed in for rho, times 2 pi r L times dr, and that simplifies even further because 2 pi al, those are all constants, they can come out of the integral. So you have that times the integral from 0 to r of r to the fourth dr. I just took my r from there, added it over there, and then that simplifies once you take the integral of r to the fourth dr from 0 to r, you get, and then multiply it by these constants, you get 2 pi al times r to the fifth over 5, which equals 2 pi al r to the fifth over 5 equals q right there. And I just solved that, just a little simplification right there. And then I'm going to use that and put it into Gauss's law, where I have the integral of E dot product dA equals the q enclosed over epsilon naught. And then since the electric field and the area are perpendicular, are parallel, that simplifies to E dA, E times dA equals q enclosed over epsilon naught. Here I can plug in, well, since we're trying to solve for E, I can plug in the dA that I got, which is just the derivative of the area, and that'll be 2 pi r times L times E on this side, equals, I'll plug in the q that I just calculated into this equation, and it'll be equals 2 pi al r to the fifth over 5 epsilon naught. And so there you have it, just divide by this 2 pi rl to isolate E, and then you can get E equals ar to the fourth over 5 epsilon naught for the electric field, for the magnitude of the electric field. And the direction of the electric field is always directed radially outwards, because here's the axis of a charge, and it'll always be going outwards. And I can't really illustrate this that much, but it'll be going down this way, out this way, and whatever view you look at it, it'll be going outwards from the cylinder. And now for point B, we're asked to determine magnitude and direction of electric field at points outside of the cylinder. So that's little r being greater than big R. And I illustrated that here. I have the original cylinder, again with arbitrary length L, with a radius big R, and then I drew a bigger cylinder, radius little r, to a Gaussian surface to illustrate the points that are outside of the cylinder. And so here I start off with almost a given, Q enclosed equals the derivative of dq. And so then I just plugged in what I had calculated for dq originally and into my integral. And so I have Q enclosed equals the integral from 0 to big R this time of AR cubed, which is the rho of R, the volume charge density, times 2 pi RL dr. And then that simplifies, again, the 2 pi AL come out because they are constants, they come out of the integral. So then that simplifies to 2 pi AL times the integral from 0 to big R of R to the 4th dr. And that equals, when you take the integral, 2 pi AL times R to the 5th over 5, and then simplified 2 pi AL R to the 5th over 5. That's your Q enclosed right there. And then once again use Gauss's law, take the integral of a closed surface of E dot product dA equals Q enclosed over epsilon naught. Plug in your numbers, plug in dA plug in 2 pi RL for your dA, or for your A at this point. And then plug in this, what you just calculated for Q enclosed, right in there. And so then you have E times 2 pi RL equals 2 pi AL R, capital R to the 5th, over 5 epsilon naught. And therefore, when you try to isolate E, solve for that, you have E equals AR to the 5th over 5 epsilon naught times 1 over R, which is the magnitude of the electric field at any points that are outside of the cylinder. And once again, it's the direction of the electric field is radially outwards. For the same reason, here you have the axis, and then you have the electric field lines are directing outwards of this almost circle. So if you're looking at it in a circle, the lines would be coming out at all points.